Good
Start.
morning, good afternoon, good evening, everyone across the globe. Um, my name is Olawole Olukunle C. I'm from Covenant University, Department of Physics, and the title of my presentation is Modeling of Electric Vehicle Motor Performance through Different Magnetic Material. I hope you can see my slide.
Yes, yes.
Okay. So,
If you can
um,
uh,
okay,
switch to the
I should
presentation
slideshow.
mode. Yeah,
Okay,
in the
okay,
presentation mode. Yes, now it's
okay,
correct. Yeah, you
okay,
can.
thank you.
Yeah.
Here is the outline of my presentation for today, background, methodology, and the rest. What is the motive of, behind this work? As we know that the world is tilting towards carbonless energy, that is facing, trying to reduce global warming by phasing out the, the fossil fuel. So as we know, EV adoption intensified the need for motor with high power density and low losses, as quoted by Geo et al. 2023. And this electric vehicle that we are talking about cannot come to existence. It will not, cannot be materialized without magnetic material, because without magnetic material, we cannot achieve it, because that means there will be no flux, no rotation, no magnetic force, and no torque and motor. And as we know, real hard supply risk and cost variation has made us to venture into this study. So what we are saying is that there is no particular material that can give everything that we need. So we are now trying to integrate all the three materials that we have used in this study. So here is the methodology, the framework. We have done this work in MATLAB. We have done it computationally, and here is the input data. These are established data from literature. Magnetic loss mechanism, relative permeability, density, conductivity, relative cost index. And at the end of the whole simulation, we got the torque, which is very important for the electric vehicle, efficiency, weight, and cost index. And here are the equations that we have used for the modeling. The torque, here is the formula. Here, yes. And we have determined, all the parameters has been stated here. The hysteresis loss in the core of material, hysteresis loss in the constants of the material, Fe is the electrical frequency, and the rest. These are the parameters that we have defined. So I move to the results. In figure 1, the torque comparison. We have compared niobium iron boron and nanocrystalline alloy and a soft magnetic composite. We have compared 3 of them. And in terms of torque, we can see that niobium iron boron has the highest in terms of torque, because the motor the traction motor needs strong torque to make the shafts rotating and to grip, without slipping. And in terms of efficiency, what we found out that nanocrystalline alloy outperform all other materials that we have simulated together. Yeah, it outperform niobium iron boron and a soft magnetic composite in terms of efficiency. And in terms of weight, we can see that nanocrystalline alloy is championing these weights. That is, it has the highest weight, followed by niobium iron boron, and last but not the least is the soft magnetic composite that has um, less weight, which is very interesting. And this is what we are trying to say, that it will be better to incorporate all these in terms of torque, at this rotating magnetic field, that we make use of a neodymium ion boron. And when it comes to efficiency, we adopt nanocrystalline alloy. And when it comes to weight, then we go with a soft magnetic composite. So in terms of, also in terms of cost, we can see that soft magnetic composite outperform all other, because neodymium ion boron is very expensive here, looking at the charts, and followed by nanocrystalline alloy. So we can see that in terms of peak, torque to weight constrained by cost and real supply, that is is not that in essence. And in terms of nanocrystalline, we have adopted iron, silicon, neodymium, copper, that in terms of belt efficiency, cost, competitive cost, marginal area, and soft magnetic composite, Somalian type, iron powder has the lowest weight, moderate torque, compelling for compact and low cost design. Because when we talk about traction motor, we are talking about the status and the rotor. So in terms of the status, where our study is trying to advise that we use nanocrystalline and soft magnetic composite, and why in rotor, why in the rotor we should adopt neodymium ion boron. So we are saying that no single material dominates across the criteria. That is, it will be better for us to go hybrid. So here is the cartoon of our work. Here is the diagram showing in figure 5, the inner structure of EV traction motor. In conclusion, we can see that this computational model has provided quantitative lengths for magnetic material selection. Nanocrystalline alloy excel in efficiency at reasonable cost, neodymium lead in torque. So we are saying that hybrid magnetic strategy will be a viable candidate for EV power trains in terms of sustainability and high performance. So here is the future work, what we are intend to do. We are planning to adopt final elements modeling, because we have used a simplified model in this our study. So we are now planning to adopt a finite element method, and also to check sensitivity analysis in terms of cost and weight under supply scenario. Here are the references, that we have used for this study. I would like to acknowledge the Center for Research, CUCRED, Covenant University Center for Research, Innovation, and Development, for financial support to actualize this study. Thank you for listening.
Thank you, Olukunle, for the nice talk.
Thank you.
Yeah, so this is one of the unique talk. We don't generally get these type of talks in magnetic conferences, and also means I think you are one of few who are representing the African region to this conference. So in the contributed talks, so much congratulations to you as well. So now we are open for the questions for this. So I have a question. You talk about in one of the slide about this NDFEB that gives the maximum torque. You talk about the maximum efficiency in some nanocrystalline alloys. Yes. So do you also do some sort of thermal stability analysis in such things?
Uh, Actually, from literature, from literature, we have found out that because we use data to
Mm,
to perform this modeling. So from literature, we have found out that nibinium ion boron has a uh, um, actually we did not check actually, but
okay.
that is the essence of this work by incorporating the three by
Hmm.
incorporating the three in terms of the efficiency, because we are trying to reduce the hysteresis loss and eddy losses.
Yeah.
That is, if we adopt soft magnetic composite for the
Hmm.
status,
Yeah.
yeah, because everything comes from, I mean, the traction, how the traction motor works is from the battery. The current from the battery goes to the inverter, which we invert it into three phase, and from that, it will go to the starter where the rotating magnetic field we
Hmm.
we come out from the air gap and connects, and it will be sustained by
Hmm.
the magnetic field from the rotor, that is from the nucleon ion boron.
Okay.
So we just base our work on the literature. Actually, we did not consider that thermal, yeah, that
But
this
for
soft magnetic has a low thermal
the
losses. Yeah.
EV application, I think this thermal stability, this aspect you consider generally or not? Means
Okay.
you consider it, right?
Okay.
Okay,
Yeah.
okay. And also you talk about the modeling at last in the future work.
Y-
So how do you
yes, sir.
model these? Using COMSOL, MATLAB, or what sort of software you use?
Yes. In this work, we have used MATLAB. So in the
Okay,
future, we are trying to use MATLAB and console multiphysics. That is
okay.
that's what we are planning. Yes, sir.
Most popular FEM simulators. Okay.
Mm.
Uh, any questions in the chat box, or you can raise your hand. Uh, we are having 1 minute, still 1 minute. Okay. So thank you,
Thank you.
Olukunle, for the nice talk.
Thank you so much.